And then we have our last speaker, which is Finley Quinton from the NTNU, and he will give us an introduction on his topic of where he just started his PhD and what's his PhD plan.
Yes, hi everybody. So I'm still relatively new on my journey of handing in my PhD in about 3 years. So I don't have too many finished up results, but I'm going to present to you what I'm working on. And actually Pascal Hoffmann is my co-supervisor, and I will be staying here for 3 months at the Fraunhofer Institute to work on this. So I'm from NTNU, which is Norway's largest university. It's called Norwegian University of Science and Technology. And for those of you who don't know where that is, it's in Trondheim. I put a little snapshot on the map here. If you're not familiar with the city, I wouldn't be surprised. And this is the main building on the top left. So that's how you probably imagined northern Norway or middle Norway, lots of snow. But just to prove, in the summer can actually be quite lovely there, so I can recommend to visit, and there's sun, and actually a lot of it in the summer, and it's a beautiful city, and actually the campus is right here on the left on the hill, and this is what we call always the old Hogwarts building, and if you walk into it, you will know why. So about me, my background is in physics. I started in February, my PhD, and in the beginning you also have to take in always some courses and everything, so it's a bit of a slow start, but my preliminary title is in Efficient Variational Quantum Algorithms for Optimization of Energy Systems Under Uncertainty. Like already said, Dr. Pascal Hoffmann is going to support me on this journey here, and I will be here for 3 months working on my first topic. However, mainly for my quantum optimization task, I'm looking into applications for energy systems, so which is a big topic in Europe at the moment and also Norway, as the energy demand is constantly increasing, and especially with the introduction of more renewable energies into the power grid, we are facing more uncertainty and more volatile situations in the grid as a whole, and often fast solutions are needed. And many of these problems we experience in the grid can be boiled down to known graph problems, where some of these are especially suited for quantum applications. So the energy sector is, a sector that's starting to get more and more interested in what quantum computing or quantum optimization can actually do for us. So for my first topic, first paper, I'm actually looking at QAOA. We heard already a little bit about QAOA previously, but just to summarize, it's called the Quantum Approximate Optimization Algorithm. It's a combinatorial optimization. It's suited for combinatorial optimization problems. It's a hybrid algorithm, and it can be basically seen as a trotterized version of quantum annealing. And the main idea is to alternate p times between layers of where you have a cost Hamiltonian that encodes the specific problem at hand, and a mixer Hamiltonian to explore the energy landscape. These Hamiltonians are quantum circuits, and these are parameterized and optimized classically. So this is why this is a hybrid algorithm. And here specifically, the first instance I'm looking into is solving the minimum vertex cover problem, which basically is you want to find the smallest set of vertices that contains at least one endpoint for every edge. Just to show you like 2 graphs here. It's already solved, so you can easily see it for small graphs, and why there are polynomial algorithms for specific easy graphs. For general graphs, it's an NP-hard problem. Yes, and the reason why I'm looking into this problem is, one thing is interesting, the objective function is linear, but it is a constraint problem. So how do we efficiently encode the constraints into QAOA? And there are mainly 2 methods to do that. And one is the penalization, which we also heard something about previously. But the problem with the penalization is it makes the energy landscape quite rugged and quite often hard to explore, and you have to know the penalty factors. And that is not known previously, and you have a complex problem you don't know much about. This can be a very hard task, which you also have the problem when you actually solve things on D-Wave, is how to choose these penalty factors. So either you can do trial and error, or do use some smart tricks to get those. But then there's another method which I'm far more interested in, which seems to also work a lot better, and that are constraint-preserving mixer Hamiltonians, which basically says if you start off in a feasible state, you can rotate within the only feasible solutions. Yes, so just to show you for a certain graph for this specific problem, so every so the idea is again the smallest set of vertices that contains at least one endpoint for every edge. That's the constraint. It's written down there again in the formula. So xu, xv has to be larger or equal 1 for every x and u connected by an edge. And so up here for this graph, for example, the corresponding constraint-preserving mixer is shown to you in the right in red. So if you look, for example, at node 5, 5 is connected to 2, 0, and 1. So what we can do is you take, do you see the mouse here? So looking at this, for example, you have the connection. So you can do a 3 controlled rotational gate onto qubit 5, or here 4, it's numbering wrong. And basically you preserve this constraint, so basically see if all other connections are within the cover, then I can rotate this quantum, this qubit by a certain rotation. For this to work, however, we have to start in a feasible state. And for the minimum vertex cover problem, the easiest state you can prepare is just put everything into the cover. So basically you initialize all your qubits with an X gate, and then you have everything as 1. This is the worst solution that is feasible, but it's a feasible solution. However, what I'm looking into is we can do definitely better than that. And one way, for example, to do this is to start off with, again, all 1s, but then apply the mixer Hamiltonian without a parameter 1 time to create a superpositional state of all feasible solutions, which you can bias by, for example, the weights of your vertices, if you're looking at weighted graphs, which I am. And you start off then with that, and I'm seeing definitely improved results, because the main idea is also to keep the circuit depth low. The hardware, because our quantum hardware is honestly kind of still sucks, so we have to keep it as low as possible. Try to keep the P, so the amount of layers we use in QRA, to a minimum, and rotating just in a feasible subspace is an efficient way of doing this. But then I'm looking into also these multi-control gates are very expensive to actually run on a quantum computer. So I'm also trying to figure out if there's a more efficient way to encode these mixers actually on the hardware. And if we can maybe do these operations in a more efficient way and reduce the amount of gates that you actually have to apply, and then see how all the scales in comparison to penalty methods and a few other tricks. But however, this is not all written down yet, so my code is currently still running on the cluster, so I can't show you too many things. And then next would be to take all this knowledge and then try to tackle a stochastic problem or a problem under uncertainty. And the question we're asking ourselves is, how can we use the stochasticity that we have in quantum computing and encode a stochastic problem onto maybe a QAA, a variational quantum algorithm, or maybe even on a fully quantum algorithm if this didn't work properly. And there are different ways to handle optimization under uncertainty. Stochastic optimization is one of them. So we wanted to check exactly which one of these are most suited and might show real future potential in solving these problems on future generations of quantum hardware. Yes, that would be it from my side. Next time I can show you my results, hopefully, and thank you for your time.
Other questions to Finley?
Thanks for the interesting talk. I think kind of also very interested in that topic. But I wanted to ask a bit about that slide. So you're saying that you want to start from applying a mixer for a certain time between certain angle, but without the parameters. What is the difference as compared to I just start with a normal QA plus 1 layer?
So the thing is, for this specific problem is actually I noticed usually start with the cost Hamiltonian, and actually for this I was in an eigenstate state of my problem, so actually applying the cost Hamiltonian first time just added the global phase, so it was actually useless to apply it. at the beginning. So I was like, okay, let's throw this out and start with the mixer. And so basically, I just wanted to start with initial state that is a superposition of all my feasible solutions. So if I start with all ones and then apply my mixer with certain fixed rotation one time, I would create a superposition over only feasible solutions. If that was your question.
Yeah, I guess when you say that we accumulate certain phase, when we start with the problem Hamiltonian, it sort of helps because afterwards you apply mixer Hamiltonian. It does not just redistribute probabilities, but it also redistributes probabilities between like from worse to better states, hopefully, right?
Yes.
So it sort of makes sense to accumulate certain phase differences at the first stage. I guess. So my question would be, yeah.
So the idea is this is the worst possible solution that's feasible. So this is pretty much probably as far as you can get in feasible space from your actual solution you want to. So why not start with something that is already a superpositional state of your feasible ones?
This way, is it the same as having p+1 layers in a random angle?
No, because what I'm doing in this specific case is I have a weighted graph, is I don't have a beta, so I don't have to optimize any beta. So QAOA does not optimize any betas for the first layer because it's my initialization.
Yeah,
it's my QAOA ansatz.
The first angle to the random value, would it be the same?
If I fix the beta and then, yeah, I mean, that's basically what I did, is take the beta, but then replace the beta with actually the node weight of my weighted graph.
Okay.
To give basically a bias superposition of all my states. And I see that the algorithm actually performs very well, too well on the graphs I've been testing previously. So I now came up with especially hard problem instances, hard graphs and larger graphs to see how this scales now for larger N. Yeah.
Question about your question. Like the difference in regular QAOA and the mixture is the stable actual pressure. Yeah, but you just replace every mixer with this. So this is
Yes, several papers by Hatfield, right, when they specifically explore visibility preserving mixers.
Yeah,
they use the same abbreviation but different meaning, right? It's a quantum alternating
Yes, yes. I mean, the abbreviations QAOA is hell when you try to get into it because people calling QAOA, QAO plus, and then Navabon is also calling it QAO plus, and then this is the same algorithm, this is a different one, and you have to dig really into differentiate all that literature from each other. Yes, but yeah, the quantum alternating operator ansatz is also short QAOA, is basically the broadening of these algorithms. Yeah.
Another question regarding the circuits you get here. Are there any plans of optimizing those circuits? The next calculus, or because we have like more than 4 or 5 control gates?
Yeah, that's exactly what I'm looking into. So one thing you can just throw it at the Qiskit circuit transpilancy and hopefully gives you something out. But I'm also working with another PhD student on this who's been looking into how to keep the gate operations smaller for these control gates. So that's the next thing I wanted to do, is try to reduce exactly these hardware requirements, but I don't have any results on that yet.
Okay, so there are no obvious starting point?
No, not currently yet. Oh, my next talk, hopefully, I have something for you there. Yeah.
Because it's also very interesting to me. Sometimes we can have a nice mixer Hamiltonian that they are expressed this way.
Yes.
I'm not even sure we can do it in really mature features. At least talking back to there is no also.
Yes, exactly. So one thing could be looking at graphs that match very well the hardware layout of the quantum computer you want to run it on, but that's kind of a bit cheating, isn't it? But yeah, so this is actually an issue, yeah.
we also try to is it something that you make? Are you with this superposition?
Yes. So basically, it's not part of the QAA. It's part. I put this mixer one time with fixed angles into the ansatz. And then I use for the rotation actually the weights of my graph to bias it towards the actual how the graph looks like. So basically it starts off with certain solution that might be a bit better already. That is the initial state. So it's warm starting with graph information and then run. And then I noticed that I need very few amount to like it performs very well on depth 1 and 2 already and finds almost always the optimal solution. So I'm trying to look at larger graphs now, more complicated, special instances that are very hard to solve. Yes?
We can make a whole seminar about it. You mentioned uniform superposition. Did I mishear you?
It's not uniform.
So
it's biased, yes.
Right?
So so it's a different superposition because I'm using the node weights.
Yeah, so we don't know what kind of probabilities do we get at the end of the day, right? So it's just some superposition.
Yes, but the nice thing is you can get any graph and you can easily create this mixer very easily this way by just plugging this in. So basically my code is also set up. I just throw any graph at it and it runs the entire thing. So no more analysis, no penalty factor analysis has to be done, whatever. So you just take the graph and you can solve it.
Okay, I think then there's no further questions to Finley. So thank you again very much. And you're again part of the organization team. Okay, and I think with that, we are at the end of the session. So thank you very much for participating today. I think it was a long day for some of you, and maybe for all of you. I heard that some flew here to early in the morning. So I think it's time now to get a rest from the quantum world, go back to the real world. And yeah, I wish you all. We have microscope eyes. But yeah, I wish you all a pleasant evening. Have a good rest. I think I'll send to you some recommendation for restaurants. Maybe you can go there in groups and have a nice dinner together. And we see each other tomorrow morning at 8 a.m. where we resume our, I already said the quantum groups. So yeah, then have a nice evening. See you tomorrow.
What you were doing, our studies are from the neighborhood of your solution. So and it was nice. So really all your own lots of fun. Thank you. Yeah, maybe initial state preparation. Yes, so for us, it's yes, basically the red one now initial state preparation. Yes, initial preparation. It's by doing next, then it makes them then right. So nothing is updated on the first one, the base rate. Different angles for different stages in the state preparation. Yes, which are
Yeah, so what we would do is you were very like a superposition of visible states that are in the neighborhood of all ones, but skewing the probabilities.
something was for both something or something. So compared to middle, the only problem is like how expensive it is. But on the other hand, I think I get this, especially for this, I get it.
Yeah, because
So I think it's then very
we can try to design instances where all ones in the neighborhood. We think about neighborhoods.